Okay, that's good. Okay, looks like YouTube is up. So today we are going to look at Opencl kernels inside of the Vitis linker. So Opencl is just another way to use the HLS. And the idea is that you're going to leverage kind of these. Hopefully, I don't know what's doing under the hood, but hopefully they have like an optimized Opencl to HLS conversion, which will operate, a little bit more effectively than trying to write the C. If you just be able to write it parallel, also to leverage code that you have for a GPU and place it onto an FPGA and see how it works. So today we're going to go through some examples and maybe try a few, and potentially another time I'll take some other examples I've done for classes, and we can try to do it on FPGA and see what it does. I would love to get it on the Versal. I'll have to figure out how we can get access to a Versal device and show off that stuff. But for now, let's go see what it looks like on our little. I think we got the ZCO 104 example that we're working on. Okay, so let's walk through a little bit of the examples. Okay, so I'm trying to see if there's anything good. Opencl supports Opencl. They just talk about same system. Okay, is there anything else to talk about Opencl before we move forward? Kernels, Opencl. Yeah, I don't really see anything special about Opencl. Okay, cool. So we're gonna go to these examples. These examples, these are Vitis Excel examples. We want Vitis Excel doesn't work anymore. Yes, we can see what their examples. Okay, let's hit up the version. I want to see if the Xilinx Opencl examples are in Vitis tutorials. The other one, Vitis library, right? Do we have Opencl here? Um, might have it one of those. Let me go. No, not in there. Meta. Might just be referencing the L1s. Kernel says Opencl. No, that's still. Yeah, I don't know if we're gonna get a CL file. Okay, yeah, so I'm not sure we got any Opencl examples here. Is there any keywords? Let's see. If we go, we're going to walk through the Vitis examples, but let me see if we open up a keyword we can look at. Let's can just see if it has the attribute. I don't have any other flags here for like XCL. Yeah, I'm not sure that has any kernels there. Vitis tutorials. Oh, look at that. We got controlling reference hardware acceleration features, controlling Vivato implementation. Versal custom thin. Oh, we have a kernel there. Yeah, so not much. Right here, Opencl. Let us do all the Opencl files. Yeah, they only got 2. And do you have Opencl? None. Curious about you. Vitis examples. Are they all in this directory? We have a few others as well. Mat multiply. Okay, looks like, yeah, let's just go through the Vitis examples here, and I think they're going to be good. Okay, so let's go ahead and read through some of these. We have this guy working over here. We'll go look at what we did in a second. I'm gonna have it build in the background while we talk. Okay, the basic structure of a vector add. If the number of loop iteration are known, tool cannot report the loop latency. In this case, we have a loop trip count can be used to specify a minimum maximum number of iterations to help the tool analyze the loop latency can reduce the total latency of the application. So we specified the same length. Loop iterations are done on a CPU. It will take multiple cycles for a new iteration to be a can pipeline these iterations to do attributes used to implement pipeline to and to mention initiation interval. Yeah. So you're pipelining. Looks like HLS all over again. Rather than reading individual items for addition, buffers are created in kernels look at multiple single burst. This is done to achieve low memory latency. Okay, interesting. Let's see. I want to see if we go to here and go to build, go to reports. Let's reports, synth report. Okay, right. Latency 1, cycles, interval. Can go pretty fast. There's no on the pipeline one. Did we not pipeline this one? I thought we had the pipeline. Right? We have pipeline. Let's see what the vector add looks like in this guy. Bugs. Add HLS report. Pipeline type data flow. Wonder why this one didn't come through, because that report just that wasn't able to pipeline it. Weird. Is there anything special of this new version? No, I don't know why I didn't seem to pipeline it. Whatever. Back to Hello World. Yeah, I'm expecting to be pipelined. It's not pipelined. That's kind of sad. Okay, we want to look at what guess we can start from the top and see what we got. Yeah, mat multiply. This one will be interesting. Max size. Okay, okay. So when you do OpenCL and CUDA, you have this idea of like blocks and breads and stuff like that. And I don't see them doing that in this. I guess they're doing the partition here. A naive implementation. Okay, now here we have these temporary partitions. What's the difference between max size? Okay. Solution. Interesting. We should see how this one comes out. Okay, it's doing the rerouting. I might open up and see what that looks like because hmm. So that would be a fun one. We should keep an eye on that one. Third one that'd be interesting. Yeah, let's try data flow. Data flow do. So we have an adder. Generates data flow attributes to implement, i.e. multiple functions can be pipelined to increase the throughput of the design. I guess you're just flowing from one to the other thing. What do we have here? Flows like that. And we're just buffer out. Vector addition using these type of function. Wish they had like some, interesting information about this so you know what's happening. Reordering. Systolic Array. Interesting. Okay, where are we going? Global memory 2 banks. We created into different DDR global banks. Not really sure what they mean by that. Let's see. Don't really see it in this situation. Where are they talking about the DDR? DDR. Okay, it's just using different, connecting it. That's just a manual configuration. Okay, nothing interesting there. Loop reordering. Better initiation interval. L reorder. So do we add anything for the reordering, or is it just script count? This matrix multiply, grabbing data from A and B. A and B are only 32 wide though, so not terribly interesting. Oh, sorry, writing the bit stream. Look at that. We'll have to open that project. Um, yeah, so this is another one, another matrix multiply. We should maybe do all three and see which one we can get. Well, this one definitely has the biggest, so this one's. This doesn't look so much like OpenCL though. Okay, then we're multiplying it. Yeah, that might be a fun one to try. And then this one was interesting, Systolic Arrays. Okay, it's performed. Array, do allows to multiply low code to perform parallel, that's speeding up loop. Number of these parallel number of DSPs in the FPGA. So do we go to hosts? They don't Opencl Examples. And they don't really give us much more, do they? Yeah, we should try the systolic one. Yeah, we should try to do the systolic one. That one would be. Okay, we built, so let's look at how this one is doing. The build finished there. So let's go open that. Why it's opening, we will build the new Opencl kernel. Where is this project? Space. Have to chase it down. I'm gonna chase it down. We were in this one. And then we'll go to the hardware link. link Botto project. Okay, that's opening. Let's update. So we got that. We're gonna go to our source code for Opencl. Paste. Why does it not like the attribute? Name. This is Opencl. Because it doesn't like those. Okay, let's try building it. Seeing what we get out of the log file. We should see some pipelining, I assume. Yeah, is there anything else useful in the host software? Care about the host software? Software gold. We have the CL functions. That's where it comes from. We have like a make HLS. Nothing really useful. Anything? Yeah, I think that should be good. Pipelining results. Okay, then it worked then. So if we go to hardware, and we go to reports, right? This pipeline type, no. This pipelining route. Okay, so we did use 35 of our DSPs, which curious to. So this is the previous design, right? And we have our vector add right here, which is using the 3 different access points into the device. We did max out the memory size on this one. We look at where the data ports are. I'm using 31 data ports. Let's try to do wide data ports now. That's cool. It's using 35. I'm curious to how much we have available. Apparently. Okay, so I guess we'll the easiest way. See how long it takes to open that up. But let's go back to the kernel, right? Where's a max size of 12? Maximum array size. So it's just well, let's try. So we're going to increase it by, we increase it by 33%. Will we see like additional 12? So maybe close to 50. Let's see. And their way, I guess we're not really doing much wise, but max, yeah, build, report, utilization. Summary, we're not using any of the DSPs, so we can go to 100. Okay. Oh, I don't. How do you optimize for size to reduce? We have, that's interesting. We should do O3 and see what happens. I'm curious about that. It's weird that our HLS has hardware optimization flags. That's really interesting. And I like how they it's really interesting. Port level hardware. We tried okay, did this update? Oh, we're at 62 now. Okay, cool. Cool. So that was almost a double increase. So we probably could just go to what, 20? Let's see, highest level of optimization. I want to know what this builds. And I want to see how that affects our DSP utilization. So I don't have it. I'm curious to see how I probably just have to a scenario. What is be 16 times 16? 256. That makes sense. Um how many multiplications are we doing? We have 256 times 256. I think it should be times 2, right? Plus an add. Yeah. I think it'd be faster. Hmm. Okay, we finished. Did we increase at all? No, we did not. So let's, it's probably good for now, right? If we increase our kernel size by anything drastic. Yeah, let's go ahead and see. We're gonna close the project real quick and start the binary container. I still want to look at how this kernel is supposed to be doing something like this, where it does systolic arrays. Systolic 3, 2, and 3. And it just connects them. The previous sum, handle boundary conditions, write back local result. Okay, so a value plus last local CI. Then how are we passing these things forward, right? How is it just the I and the K somehow we're passing forward? The K value, the I value, and the J value. Okay. Okay. We have created the BD and they've updated. We'll look at it while it builds. Here's our matrix multiply. Our 3 gems. Our general memory, I guess. Address. Data is 31. I guess we'll have to increase the data, but I'm not sure there's a point. Try to manually increase the data if that changes anything. How about you? What data size are you? Not telling me? You, I assume, are pretty, yeah, 128. Okay. Local block. Oh yeah, that makes HLS a lot easier. They were doing the block level stuff now. Did we let it run? I mean, we already let the other one run. So yeah, there's a lot of interesting things to do, but I don't these aren't necessarily the what we would see in other things. Well, what would be interesting is to understand the AI kernels. This is just an AI adder. And you learn how to write in minimal C for these codes. We have different inputs and outputs. Oh, that's the tester. Input stream, output stream, operator plus. Where do these commands come? Those feed things through the port. Okay, that's just your average connectivity graph. Is that all they have? Do I need to go newer or straight up master for AI kernels? I guess we would have to go to the other Xilinx thing for AI kernels. That's going to be what the Vitis tutorials, AI engine development, feature tutorials using GPIO. We would have to go through these. I would love to walk through these. We need to get more LeanNet. That's gonna be hard. Get hardware for yeah, that's the LeanNet. Why is it not just using the knock? I'm really confused by this picture, right? So like look, if we look at this picture, right? We have our AI engine and we have the knock. And the HLS is grabbing information from the knock and feeding it to the AI engine. But what if I want the AI engine to be connected to the knock, right? Like, is there an issue with that? Is there um RTP runtime? Okay, yeah, here's the knock. Do we have to use those streamers? We just connect directly to the knock. Why are we not using the knock? That bothers me. To traffic generators. Maybe it's that one. Maybe it's that one. That one. Ooh, the fur filter. Good. 9 tutorials. Okay, let's see what we got here. Using GMIO. Okay. Just working with knock. Whoa. Different things. We have a connectivity for filter. Cool. Setting. We just let it connect on its own? Maybe. I don't know. I want an example where they connected or not. Yeah. Okay. Anything to. This is still doing the block level stuff. And I bet, yep, that guy's still going because he's big. We go look at the log. Him. Oh yeah, subscriber. Cool. Thanks. So, okay. Are these OpenCL? My question in all this: are these OpenCL kernels any better than if we did it on our own, right? So this one looks relatively nice. If we did these on our own, could we understand pipelining, trip count? I think this is just our two C size times C size. Oh, the maximum trip count. We're giving it a very specific value. Okay, we understand a trip count. Mention. Okay, assume a square matrix. Max dimension. Dimension. Go through to the values, burst right. Yeah, I'm not seeing anything terribly interesting with these. So this has the reordering and partitioning in it to help. I feel like the systolic array thing, so I wish it was easier to follow. But yeah, I don't think there's much else we can talk about in this situation. Oh, we could look at the driver software. Let's look at the driver software. Does an OpenCL have special driver software? I can see that being an issue. So we go here, IP, driver. That's normal HLS step, normal HLS, normal HLS, address of A, address of B, address of C, empty columns. Yeah, that looks like about it. Get A, get A. Is the 0. Useful. Nope, nope, nope. Let's see. Not necessarily doing Linux. Curious how. Find from file. Initialize and a release. But where do you define the values? Oh, I guess you get the instance name and then you can pointer by it. You're just requesting it from Linux. Interesting. MDD. There. Oh, look, it finished completely. 77. Okay. Well, I'm gonna have to think of some ideas about Opencl because it's just not translating from other examples. Like if you look at what Opencl Examples, and let's just do. Oh, actually no, let's do Opencl. Really good matrix multiplication example. Is it? Yeah, good example. So let's go through this. Don't we have these global IDs, right, to handle threads? Kernel have these values. And it's not like we can just copy and paste this kernel in. Oh, we could copy and paste the kernel and see what happens. Right? Wait. The whole goal of HLS, right, is to copy and paste and see what happens. Can we see if the tools will let us do it at the same time? Hey, I have a kernel here. Boom. Yeah, just go ahead and stop that. Okay, so go to project, right? That one and add gem. Yeah, I am curious to what my gem will build. So if I copy and paste this, what does this give me, right? Global IDs. How does the hardware handle it? If it works, that will be interesting because you just copy and paste Opencl. That's the whole goal of HLS. Okay, it worked. Let's go see what the report says. HLS report. It doesn't have any clue what's going on. No clue what's going on. It could be big, it could be small, it doesn't know. And it's just like, I'll do a little bit. So the max size is important. But let's go ahead and do kernel 2. Okay, this one has barrier commands. What do you do with barrier commands? I want there to be an error because we're doing very processory things. Like, does it have a local ID? Does it have group IDs? Does it know? Does it know what how to tile things? Undeclared. Yeah. Where's the K and the TS come from here? This TS. Or TS tied TS. We'll just say TS is 32. Right? We'll just say TS2. Right? We're going to assume 32 by 32 kernels. We could try to set these constances. Okay, build gem2, and ports. Has no clue what's going on, and it builds that much. So what we're gonna do is we're gonna go to let us go back to this guy, yeah. And we're gonna do like a find max size. How does it work here? I did these max size. And fine. We'll do max dim. Say 32 to start with. And what we're going to do is we're going to take these three variables right here. We're going to say everything is identical. We have now that we have this max dimension, let us build. And before what we did DSP. Okay, cool. So finished. Do we need to open the report? Um, let's try that one. So I'm not seeing anything useful here. We have a directive view we can add. Window. What are these little windows called? You can get them here. Overview. Be under HLS. Here we go. Links. Terrible. Is able to pipeline something. Yeah, I don't really know what it's doing here. VRAMs mostly look like they're being used for storing the devices. Okay, well, let's try adding those kernels, right? This situation be 32. It really does not like that. In this for loop, I'm gonna do 32. And let's see if that. Oh. So now we're like, hey, don't worry, your trip count will be exactly 32. Don't worry about it. Tiling in FPGA design doesn't seem very interesting. Oh, yeah. Yeah, I'm curious. I understand how global ID works inside a GPU. I'm curious to how global ID works inside a FPGA, right? How does an FPGA do IDs like that? It's confusing me. Okay, let's see. What is your report? Did not help whatsoever. Okay, so I don't think my OpenCL is not a drag and drop in this situation. Maybe with the AI engines, but no. I it's just another form of HLS, just with some slight different coding caveats. So I'm probably gonna have to. I don't see any good way unless you can effortlessly port some of these libraries into the system. I don't think it's working. Hmm. Oh well. I think we're gonna call it there today. We can add modules just fine. And the goal is, I think, we'll do a primer, but when it comes down to the advent of code in December, we're going to do it all with this HLS platform. Do it rapidly and see how it works. Okay. Yeah, so I'm calling it a night.